Alright, hello there. So today we are going through problem 3, weighted quick union. Alright, so let's just jump right into 3a. So 3a is saying that we have a weighted quick union object in the left column of the table below, and we want to fill in the parameters for these connect operations on the right column, or determine if the object is impossible to create. So I want to go over a few conventions before we jump right in. One is that for weighted quick union objects with two trees of different sizes, the root of the smaller tree is linked to the root of the larger tree. So let's just do an example. If we have something like 2 linked to 1, and we have something like a lonesome 3 here, and we called connect on 2, 3, 2 belongs to the larger tree with root 1, so the root of the smaller tree, 3, would link to the root of the larger tree, 1. So it would look like this. The second thing is in the second statement here, which says that in case of two equally sized trees, the root of the left argument is placed below the root of the right argument. So if we had these two equally sized trees, we called connect 1, 2, then we would have 1 linked to 2 like this. So 2 would become the new root of this size 2 tree. Alright, so let's just jump into the first part. Looking at this object, this should ring some alarm bells immediately. So one thing is that when we call connect twice like this, usually we don't get an object like so. We get an object that looks like our example 1 with this structure. So already we can tell that this is probably not going to be possible to do, but we can walk through it one by one to see how. Alright, so we have two options of calling connect. One is that we can call connect 3, 5 first. So let's have 3 connected to 5. And then the only other option we have is to call connect on 3, 2. And since 3 belongs to the larger tree that has root 5, the 2 would would link to this root instead of linking to 3. So that's not what we want, right? Alright, let's erase this and try the second option. Let's say we start with connect 2, 3. So we have 2 connected to 3 like so. Alright, that looks good. And then let's connect 3 and 5. Well, what's going to happen is that 3 is the root of the larger tree. So 5 will link to 3, and 3 will become the new root, not 5. This does not match what we have on the left right here. So running through these two calls, we know that this object is impossible to create. Alright, now we're going to look at part 2. And for part 2, we know that we're arbitrarily constrained by calling 2 and 4 as our first parameter in these first two connects. Okay, so looking at the object on the left, we see that 2 and 4 are connected to 0. So it makes sense to put 0 and 0 as the second parameter for these first two arguments. Alright, the trickiest part of this problem is trying to construct this tree right here. So we could possibly connect 3, 5 first, or 3 or 0 first. So let's just go the wrong way first. Say we connect 3, 0. Then we would have 3 connected to 0, and 4 connected to 0, and 2 connected to 0. So that looks good. But then when we call connect 5 and 3, 5 will connect to the root of the larger tree, which is 0, instead of 3. So that's not what we want. Instead, we should connect 3 and 5 first. So we call connect on 5 and 3 to get 3 connected to 5. And then we call connect on 3, 0. So we have this tree represented by 0 here. And what we see is that 3 will connect to the root of the larger tree, which is 0. So we have an arrow pointing from 3 to 0. So that looks like what we want. Last but not least, we're just going to connect 6 to 0, which we can get by calling 6, 0. So this tree on the right looks perfectly like the tree on the left, so we're good. All right, now let's go to B. So B is saying that we have a new operation called undo that undoes an earlier disjoint set connect operation. So we're going to see if we can use any of these implementations below with undo without using an additional data structure. So this problem seems like it'd take a long time, and it's only 4 points. So the best way to approach this problem would be to use some intuition as to why these 4 implementations would work or not. All right, so I need some space here, so I'm gonna scroll down and work on this B. So the first thing we can immediately rule out is quick union and quick find. And this is because both implementations will use a parent array to keep track of the roots of each element in the set. So as we call multiple connect operations, the indices in the array would be directly modified and we would lose the old roots since we don't keep track of them with, say, like an instance variable. So we can run through a quick example. Say we have 0, 2, 1, and 3. So we have this starting out. If we do quick find and quick union, so let's say we connect 1 and 0 and 2 and 3. So 2 is the root and 0 is the root. If we decided to connect 0 and 2 like so and have 2 be the new roots, then what would happen with quick find is that we start out with 0, 0, 2, 2, and we get 0, 0, oh actually not 0, 0, my mistake, 2, 2, 2, 2. And this is because quick find modifies each entry of the 2 sets that we are connecting to be the root in the parent array. Meanwhile, quick union will start out with the same thing, 0, 0, 2, 2, and it'll end up with the parent array of, so 2, 2, and then these 2 would be 2, and this would be 0. So as you can see, this 0 stays the same. So what is happening is that quick union only changes the entry representing the root of one of the sets to be the new root of the connected set. Alright, so quick union and quick find are no good without a data structure to call undo. Weighted quick union and weighted quick union with path compression are a little harder to see. So both implementations use an array to keep track of the size of the sets, and when connecting 2 sets, they have the root of the larger set represent the root of the smaller set. So kind of really similar to what we had in 1 here. Alright, So for weighted quick union, the best way to do this is to draw out a quick example. So say we had a structure with nodes 0, 1, 2, 3, and 4, I believe. We can call connect on 0, 3 to get this, connect on 0, 4 to get this, connect on 1, 2 to get this, and then connect on 2, 4 to get, I think, 1 to 0. All right, so say we want to use undo to revert the tree to the state before we called connect to 4. Well, this would be hard to do because we don't know whether we can call, if we don't keep track of the parameters we used for the previous connects, we don't know if we can call undo 2, 4, or undo 1, 0, or undo 2, 3, or undo 2, 0. So it's ambiguous as to which undo we can call, like which undo has an effect and which undo does not have an effect. So therefore, we must keep track of the previous arguments of connect with some data structure. So weighted quick union is impossible to implement with undo. All right, with path compression, it's actually a little bit more straightforward, and we have a similar conclusion. So say we start out with this. And this 3 is pointing to this 2 here. All right, so we have this tree. If we compress it, we get something like, so if we compress this, we get something like 1, 2, 0, and 3. So as you can see, we just lost a lot of depth and information in our tree after using path compression. So it's impossible to tell with the final tree we have here if we called something like connect 1, 3 or connect 2, 3 in the first place. And therefore, we would have to use some kind of data structure to keep track of the arguments of connect once again. So calling something like undo 1, 3 would have ambiguous results unless we had some kind of data structure. So therefore, we can conclude that weighted quick union with path compression is also impossible. So now we're finished with B. Let's move on to C. So for part C, we are using a graph to deal with the problem of disjoint sets. We will be using an adjacency list with no duplicates. This is actually pretty important that we have no duplicates to keep track of the edges. And we also have n representing the number of nodes and m representing the total number of calls to either connect or is connected. So once again, I'm going to move down here for more space, and we're going to look at the first parts, which is what is the worst case runtime of any single call to connect AB. So in other words, this is the same thing as asking what is the worst case runtime of calling add edge on an adjacency list that keeps track of the edges. One thing we want to note is that we want an adjacency list with no duplicates. So we have to check if an edge between the two nodes already exists before connecting them. So say we have these nodes A, B, C, D. The worst case scenario would be when these nodes are already connected as one set. So there are actually two ways to interpret this. One is when we have all edges span out from one node, like so. The adjacency list will look like this then. B, C, D, A, and A. So this is our adjacency list. And as you can see, to check if we have any duplicate edges, we will have to check through these n-1 nodes here before we can actually add the edge. So our total runtime is now theta of n. And actually, this is probably the best answer you can give because your max number of edges should not exceed your max number of nodes. However, since this question is a little ambiguous, we also have some other answers that can give you credit for this question. So we could have also interpreted the worst case as this, where not everything is connected to one node. So we have A, B, C, D again, but this time we have B, C, A, B, A, and B. All right, so here we would only have to check m times to figure out if we had any duplicate edges in our adjacency list. So the runtime would be theta of m in this case. So theta of n was also a plausible answer. And since these two represent the worst case possible, you can say that the total runtime, or the worst case runtime, could have been theta of n plus m. So considering both of these two cases, you would get this. So this is also a possible answer for credit. And the reason why we have so many possible answers is because this question was rather ambiguous. And there are many ways to interpret it. Awesome. So now part 2. With the second part, we are looking at the worst case for a single call to isConnected. In other words, we are asking for the worst case runtime of depth first search. And we know from slides or from lecture that this should be theta of the number of vertices plus the number of edges. And basically, we can just translate this runtime into n plus m. So n is the number of nodes, so we know this is equal to n. And m can represent the number of edges, because this can represent the number of calls to connect, which creates edges. Therefore, the answer is theta of n plus m. However, you could have also been given credit if you chose theta of n or theta of m as well. And this is because theta of n can be considered the worst case if you had a sparse graph with more nodes than edges. And theta of m could have been considered worst case if you had a very well-connected graph. So these two could have been considered viable answers, and you would have been given full credit. Anyways, that was problem 3. Hope you enjoyed this walkthrough.